All right, let's start with a puzzle. Take a look at this signal. It's a perfect square wave. Notice how it's blocky, crude, sharp. To be honest, it looks completely unnatural. Now, here's the puzzle. Could you create this exact shape using only smooth sine waves? It feels impossible, right? I mean, think about it. How can you take these beautiful, flowing curves and use them to create those sharp 90-degree angles? It just doesn't seem to add up. Enter the Fourier Transform. This is a mathematical tool that finds a hidden order even when all you see is chaos. It gives us the secret recipe. For the square wave, it starts like this. The Fampian f of t is approximately 4 over pi times the sine of t. But that's not the whole story. To get closer, we add another piece, 1/3 times the sine of 3t, and we just keep going. We add 1/5 sine of 5t, and so on forever. Okay, that's a cool math trick, but so why do you care? Because of this. Sine waves are the fundamental building blocks of our universe. And what's amazing is that every single wave can be described with just 3 numbers. First, its frequency. How fast is it? Second, its amplitude. How loud is it? And third, its phase. When does it start? When you can break any signal down into these simple numbers, you get new superpowers. You can analyze, see the hidden ingredients of any signal. You can filter, remove noise, clean up audio, isolate trends. And you can compress. This is the magic behind JPEG and MP3. You just keep only what matters. The algorithm that gives you these powers is called the discrete Fourier Transform, or DFT for short. And here it is, the scary formula. X sub k equals the sum from n equals 0 to capital N minus 1 of x sub n times e to the power of negative I 2 pi over capital N times kn. Looks intimidating, right? But here's the secret. It's not complex math. It's a recipe detector. And I promise, by the end of this series, you're going to understand exactly what every single piece of that formula does. So we saw our signal, that blocky square wave, and its secret recipe. This reveals something profound. There are 2 fundamentally different ways of looking at the exact same information. 1 signal, 2 worlds. And to understand this, let's stick with our subject, our familiar square wave. It's the perfect example because its 2 views are just so dramatically different. So let's look at view 1, the time domain. This is the view you're probably already used to. It's the world as we experience it, moment by moment. It answers one really simple question. What is the value right now? To a computer, a signal in the time domain is, well, it's just a list of numbers. That's it. When you record audio, you're just grabbing a long list of air pressure values, one after another. This first view, the time domain, simply records what happened and when. For example, in this table, you can see at time 0 seconds, the value is 1. A moment later, at 0.01 seconds, the value is still 1. Then later, at time 0.5, the value drops to -1. It's just the raw data samples. But now for the other perspective. View 2, the frequency domain. This view asks a completely different, almost hidden question. What ingredients make this? Here's the key. We completely ignore the when. We don't care about what happens from one moment to the next. We only focus on the what, the fundamental components. This gives us what's called the spectrum. It's a list of our ingredients and their strengths. So for our square wave, we have an ingredient at a frequency of 1 Hz with a strength of 1. Then another at 3 Hz with a strength of 0.33. Another at 5 Hz with a strength of 0.2. And so on. And what is each ingredient? Every single one is a pure sine wave. So here is the most important takeaway of this chapter. 2 views, the exact same information. When you switch between them, no data is created, no data is lost. It's just a change of perspective. And there's a mathematical bridge that lets us travel between these 2 worlds. As you can see in this diagram, you start in the time domain with your list of samples. You apply the Fourier transform, and you arrive in the frequency domain with your list of ingredients. And to go back, you just use the inverse transform. It's a perfect 2-way street. Okay, so how do we actually create a machine that can listen to a signal and tell us which rhythms are inside? Let's build our first rhythm detector. For this entire chapter, our machine has only one job, a single purpose. It's here to answer one simple question. Does this signal contain a rhythm that repeats exactly 3 times per second? A 3 Hz rhythm. That's it. We're not trying to find all the rhythms yet, just this one. So, how does it work? What is the mechanism? The core idea is incredibly simple, and it's actually the foundation of the entire Fourier Transform. As you can see in this little diagram, we take our unknown signal, and we also take a perfect reference wave, a clean 3 Hz cosine wave. Then we multiply them together point by point, and finally we sum everything up to get a final score. A big score means a strong match. A small score means no match. Simple, right? Let's see it in action. First question, test case 1, a perfect match. Let's test our machine on a signal that we know is a perfect match. The input is a 3 Hz cosine wave, and the reference wave, also a 3 Hz cosine. When we do this, they align perfectly. A positive peak lines up with a positive peak. A negative trough lines up with a negative trough. And since positive times positive is positive, and negative times negative is also positive, the result is always positive, which means we're going to get a huge final score. And here's the proof in the code. We define the waves. The signal is a numpy.cos at 3 Hz, and the test wave is identical. Then we do the 2 key steps you see here. We create the product by multiplying them, and then we sum it up to get the score. And look at that, the score is 500.0, a really strong detection. It works perfectly. All right, test case 2, a clear mismatch. Let's give our detector a signal with a completely different rhythm, say 7 Hz, and see what happens. Our reference wave, of course, is still our standard 3 Hz cosine. This time, the waves are totally out of sync. Sometimes their peaks align, giving a positive result. But just as often, a peak from one wave aligns with a trough from the other, giving a negative result. So the positive and negative parts just cancel each other out. The final sum should be pretty much 0. Let's check the code. The only thing that's changed is the signal is now a 7 Hz cosine. The mechanism is identical, and the score? Exactly 0.0. Correctly ignored. So far, so good. Our machine seems pretty good, right? But what if the signal is shifted? This is where our simple machine breaks. Test case 3, the flaw. Let's give it a signal that has the right frequency, 3 Hz, but is shifted in time. Instead of a cosine wave which starts at its peak, we'll feed it a sine wave which starts at 0. Our reference is still our standard 3 Hz cosine. So what happens now? The result is perfect cancellation, again. Here's the final fatal test. You can see in the code, the signal is now a numpy.sine wave at 3 Hz. We run the same process, and the score is 0. This is a false negative. The rhythm is there, but we missed it. Our detector has failed. We know the 3 Hz rhythm is in the signal. We literally just put it there, but the machine is telling us it's not. Our machine is phase blind. It has a critical flaw. It can only detect rhythms that are perfectly in phase with our cosine test wave. This is the phase problem, and to solve it, we need an upgrade. So what's the simplest solution? Well, if our one test only catches on-time signals, let's just run a second test. It's that simple. Our cosine test is great. It catches the on-time signals perfectly. So to fix our flaw, we just need a second wave that can catch the shifted signals. And what's a cosine wave that's been shifted by 90 degrees? A sine wave. So here's our new upgraded machine. As you can see in this diagram, the unknown signal comes in and gets split into 2 parallel processes. In test 1, we do exactly what we did before. We multiply the signal by a cosine wave, sum it up, and get what we'll call score A. This is our on-time detector. But now, simultaneously, in test 2, we multiply the same signal by a sine wave, sum that up, and get score B. This is our shifted detector. Now, if either score is a big number, we know the rhythm is present. Let's put this to the test. Let's solve the flaw from the last chapter. Remember our failing input? A 3 Hz sine wave. Our old reference wave was a cosine, and our new reference wave is a sine. And look what happens. The old cosine test still produces a score of 0. It completely misses the signal, just like before. But our new sine test? The input signal is a sine wave, and the reference wave is a sine wave. They are a perfect match. They multiply together to create an always positive result, and we get a massive score of 500. We found it! Let's just prove it with the code. Here's our signal, an histories.sine wave at 3 Hz. First, process 1, the cosine test. We create our wave stack, multiply it by the signal, and sum it up to get score cosine. Then, process 2, the sine test. We create a wave son, multiply that by the signal, and sum it up to get score sine. And the results? The cosine score is 0. The sine score is 500. We caught it! Our machine is no longer phase blind. Okay, it works. We solved the problem. But it's a little clunky, right? We get 2 separate numbers. We have to look at both of them. It's not elegant. And in math and engineering, we are always searching for elegance. This search for elegance leads us to the key insight. The one thing that elevates this from a clunky, 2-part hack into a single, beautiful mathematical operation. And that insight is Euler's formula. Look at this magnificent equation. E to the power of negative I theta equals cosine of theta minus I times the sine of theta. It's a magic package. This is a single mathematical object that holds both of our waves at once. Do you see it? It's got the cosine wave we need, and it's got the sine wave we need, all wrapped up together. So this means, instead of running 2 separate tests, we can just run one complex test. Here is the truly elegant solution, using Euler's formula. Our signal is the same as before, that 3 Hz sine wave that used to break our machine. But this time, we create a single complex test wave. In NumPy, we do this using nonquestion.exp with a -1j. That small bit of code automatically creates the cosine minus I sine wave for us. It's brilliant. And then, in one step, we get both answers. We just multiply the signal by our new complex wave, sum it up, and we get a complex score. So what does it print? The score is 0 minus 500j. Now, what on earth does that mean? Let's decode the score. That single complex number, 0 minus 500j, gives us the complete picture instantly. The real part, the 0, is the cosine score. It's the on-time strength. And the imaginary part, the minus 500, is the sine score. It's the shifted strength. It's the exact same information we got from our clunky 2-test machine, but it's packaged perfectly into a single, elegant number. It tells us there is 0 correlation with an on-time cosine wave, but a very strong correlation with a shifted sine wave. And what we have just built, this elegant, powerful, phase-proof detector, this is the discrete Fourier Transform, the DFT. It is nothing more and nothing less than multiplying your signal by a complex test wave. And now you know exactly why it works. Remember this beast of a formula? X sub k equals the sum of x sub n times e to the power of negative I times 2 pi over n times kn. It looks scary. It looks complex. I get it. But here's the secret. It's not scary anymore. Because you already understand every single piece of it. That formula, it's just the blueprint for the exact machine we just built together in the last chapter. So let's decode that blueprint, symbol by symbol. First up, that x sub k on the left, that's just the final complex score our machine spits out for a specific frequency, k. Next, that big Greek letter, sigma, that's just our accumulator. It means add everything up. It's the summing part of our machine. Easy. The x sub n, that's your input signal, the list of numbers we're testing. And that crazy-looking e term, e to the power of negative I something something, that's just Euler's magic package. It's our complex test wave generator, spinning at speed k. It's the cosine and sine waves, all wrapped up in one. So when you see the signal, x sub n, multiplied by the test wave, e to the something, that's the core comparison. It's our point-by-point multiplication step. And finally, the sum symbol tells us to add up all those products to get the final score, x sub k. That's all it is. Loop, multiply, sum. You already knew that. Now you just know how to write it like a mathematician. Okay, reading the blueprint is one thing. Let's get our hands dirty. Let's do one by hand. Here's the challenge. We'll use a super simple signal with just 4 samples. N equals 4. The signal, x, is the list. 1, 0, -1, 0. Our mission? Calculate the score for the frequency that repeats exactly once. In the language of the formula, that means we're calculating for k equals 1. So our formula becomes x sub 1 equals the sum of x sub n times e to the power of negative I times pi over 2 times n. Let's walk through this step by step. We're going to build a table. Okay, let's start at time n equals 0. Our input signal, x sub 0, is 1. The test wave at time 0 always starts at 1, so the product is 1 times 1, which is 1. Got it. Next, n equals 1. The input signal is 0. The test wave makes a 90-degree turn to negative I, but it doesn't matter what the test wave is, because 0 times anything is 0. Then, n equals 2. Our input signal is negative 1. The test wave makes another 90-degree turn, so it's now at 180 degrees, which is the value negative 1. The product? Negative 1 times negative 1 is positive 1. Last step, n equals 3. The input signal is 0 again, so we don't even need to calculate the test wave. The product is 0. Now for the final step of the formula, the sum, we just add up that last column. 1 plus 0 plus 1 plus 0 equals 2. Our final score is x sub 1 equals 2 plus 0j. Okay, fantastic. But what does this actually mean? We got a complex number, 2 plus 0j. Let's translate that. First, the amplitude. That's just the length of this complex vector. The absolute value of 2 plus 0j is simply 2. What's the verdict? Phase. This is the angle of the vector. The angle of a number sitting on the positive real axis is 0 degrees. The verdict? It's perfectly aligned. The algorithm correctly identified our signal was a cosine wave with a magnitude of 2. It worked, but you don't have to take my word for it. Let's ask Python to check our homework. First, we define our 4-point signal in a NumPy array. 1, 0, -1, 0. Second, we run the algorithm. We call numpy.fft.fft on our signal. Third, we just look at the result for k equals 1, which is at index 1 of the output. And what does it print? The score for k equals 1 is 2 plus 0j. The amplitude is 2.0. It's a perfect match. So, the algorithm is correct. You just proved it by hand. But it is also punishingly slow. Let's talk about the real cost of this calculation. Looking at the formula, you can see the problem right away. For each frequency k, we have to loop through all n frequencies. And then, inside that loop, we have to sum over all the samples, another n samples. We have 2 nested loops. That's n frequencies times n samples. In computer science, we call this O of n squared complexity, and that is a scaling nightmare. Let's put this into perspective. For our little test case where n equals 4, that's just 16 operations. Trivial, you could do that on a napkin. But what about a small signal, say n equals 1000, just a tiny blip of audio? That's 1000 times 1000, 1 million operations. Okay, a modern computer can handle that. But what about 1 second of standard CD quality audio, where n is 44,100? That's 44,100 squared, which is nearly 2 billion operations for 1 second of audio. This is a deal breaker. It means the DFT, as we've defined it, is utterly useless in practice for any real-world signal. So, for this chapter, our job changes. We are no longer builders. We are detectives. Our mission is to find out exactly where the DFT algorithm is wasting all this time. We're going to put it under interrogation. We're going to build an evidence board. The suspect? The so-called twiddle factors. W sub n to the kn. These are those complex values from the test waves we multiply our signal by. They're the core of the calculation. Let's lay out all the evidence. For our n equals 4 case, here is the full workload. Every single calculation the DFT performs. On the left, you can see we're calculating our 4 frequency scores. And for each one, we multiply by our 4 input samples. This table shows every single twiddle factor it has to compute. For x sub 0, they're all just 1. For x sub 1, it's 1, -I, -1, I, and so on. The slow algorithm just plows through this, row by row. Now, as good detectives, we look for a pattern. Do you see the smoking gun? Look closely at this table. Compare the row for x sub 1 with the row for x sub 3. What do you see? For x sub 1's column, we have -I, and for x sub 3's column, we have +I. They're negatives. What about for x sub 2's column? -1 and -1. And x sub 3's column? +I and -I. The bottom half seems to be a strange mirror of the top half, specifically a negative mirror. This isn't a coincidence. This is the key property. Remember, these values are just points on a circle. What happens when you go exactly halfway around the circle from any point? You end up at the negative of where you started. Mathematically, that means w sub n to the k plus n over 2 equals negative w sub n to the k. Going halfway around the circle gives you the negative. This is the secret. Now we have the key, let's look at the confession. Let's see what x sub 0 and x sub 2 are actually doing. The original equations are x sub 0 equals x0 plus x1 plus x2 plus x3, and x sub 2 equals x0 minus x1 plus x2 minus x3. Now, let's just rearrange those terms, grouping the evens and the odds. Look, x sub 0 is just x0 plus x2 plus x1 plus x3. Let's call those term A and term B. Now look at x sub 2. It's the same term A minus the same term B. It's doing the same thing for the odd rows. Let's look at x sub 1 and x sub 3. After we rearrange them, we get x sub 1 equals x0 minus x2 minus I times x1 minus x3. Let's call those term C and term D. And x sub 3? It's the same term C plus I times the same term D. We found the waste. It's laid bare right here. The algorithm works like an amnesiac. It blindly calculates term A, x0 plus x2, when computing the x sub 0 score. Then, it completely forgets it ever did that, and recalculates the exact same term all over again when it gets to x sub 2. It's doing double the work it needs to. The entire point of the famous fast Fourier transform is to stop doing this. It's a divide and conquer algorithm. The idea is simple but brilliant. Calculate these smaller pieces once and use them twice. By eliminating all this redundant work, we can take a problem that was once impossible and make it incredibly fast. And the entire elegant fix is captured in two simple-looking formulas. These are the magic formulas. For any frequency k, the solution is right here. First, x sub k equals e sub k, that's the result from our evens, plus w sub n to the k times o sub k. And that o sub k is the result from our odds after we've multiplied it by that twiddle factor. Now here's the magic. Look at the second formula. X sub k plus n over 2, so the corresponding frequency in the second half of the spectrum, is e sub k minus the exact same term, w sub n to the k times o sub k. Do you see the beauty of this? You calculate the pieces once. You calculate e sub k and that twiddled o sub k just one time, and you use them twice. That's it. That's the entire secret to the speed. This structure has a famous name. It's called the butterfly, and this diagram shows you why. You take your input from the smaller problems, e sub k and o sub k. The o sub k gets multiplied by the twiddle factor, and then they combine. One path adds them together to get x sub k. The other path subtracts them to get x sub k plus n over 2. This right here is the wiring diagram of speed. Okay, that's the theory. It looks elegant, but does it actually work? Let's prove it. We're going to do a full walkthrough with n equals 4. Let's go. Okay, here's our signal. Same one we've been using. X equals 1, 0, negative 1, 0. Step 1, divide. This is the easy part. We just split the signal into its even and odd indexed parts. The even indices are 0 and 2, so that gives us the signal 1, negative 1. The odd indices are 1 and 3, which gives us the signal 0, 0. Done. One hard problem is now two easy problems. Next, step 2, conquer. This means we solve the smaller DFTs. Now, a two-point DFT is super simple. For a signal AB, the DFT is just A plus B and A minus B. So for our evens, 1 and negative 1, E sub 0 is 1 plus negative 1, which is 0. E sub 1 is 1 minus negative 1, which is 2. So our E vector is 0, 2. For the odds, 0 and 0, well, that's even easier. O sub 0 is 0 plus 0, which is 0, and O sub 1 is 0 minus 0, which is also 0. So our O vector is just 0, 0. Okay, the hard work is done. The rest is just assembly. Step 3, combine. Now we use our magic formulas. We'll start with k equals 0. Our E vector is 0, 2. Our O vector is 0, 0. And the twiddle factor we need, w to the power of 0, is just 1. So for the first half, x sub 0, we use the plus formula. X sub 0 equals E sub 0 plus 1 times O sub 0. That's 0 plus 0, which equals 0. For the second half, x sub 2, we use the minus formula. X sub 2 equals E sub 0 minus 1 times O sub 0. That's 0 minus 0, which is also 0. Look at that. We just got two results, x sub 0 and x sub 2, from one set of calculations. Let's keep going. Now for k equals 1. The components we need are E sub 1 and O sub 1. And the twiddle factor, w to the power of 1, is negative I. So for the first half, x sub 1, we use the plus formula again. X sub 1 equals e sub 1 plus negative I times o sub 1. That's 2 plus 0, which is just 2. For the second half, x sub 3, we use the minus formula. X sub 3 equals e sub 1 minus negative I times o sub 1. That's 2 minus 0, which is also 2. And we're done. Our current results are x sub 1 equals 2 and x sub 3 equals 2. So, what is our final output? Let's assemble the pieces. X equals 0, 2, 0, 2. Now, does that look familiar? Let's verify it. Let's go back to the code we ran in Chapter 4. It's a perfect match. We got the exact same answer, but with so much less work. So what was the point of all of this? The performance gap. The old way, the slow DFT, was O of n squared. It gets exponentially worse as your signal gets longer. The FFT is O of n log n. It is drastically faster. And that is the story of the FFT. We went from beautiful theoretical math to a world-changing tool. By finding and eliminating that one source of wasted work, we unlocked one of the most important algorithms ever discovered. You've been on an incredible journey. Let's just take a moment to look back at how far we've come. Let's look at the journey. First, there was the puzzle, the impossible puzzle, making square waves from smooth curves. Then we built the mechanism. We created a rhythm detector from scratch using a simple multiply and sum idea. Then came the upgrade. We introduced phase and complex numbers to solve a critical weakness in our machine. After that, we found the blueprint. We decoded the formal DFT and realized it was just the plan for the machine we'd already built ourselves. And finally, we did some detective work. We found the waste in the algorithm and figured out how to eliminate it. The result of all this? You now own the algorithm. You don't just know how it works, you know why it works. But here's the billion-dollar question. Why is this algorithm the engine of modern life? This speed is the engine behind everything. Let's talk connectivity. Your Wi-Fi, your 4G, your 5G connection? It uses the FFT to untangle hundreds of signals all sent over the same frequency. It's magic. What about compression? Your MP3s, your JPEGs, the video you're streaming right now? The FFT is used to find and delete all the invisible frequencies you can't see or hear, making the files tiny. In medicine, MRI and CT scans, the raw data they capture is pure frequency data. The FFT is what turns that raw data into the images a doctor can actually read to save a life. And recognition. An app like Shazam? It's literally taking a frequency fingerprint of the music in the room and matching it against a massive database. That's the FFT at work. The fast Fourier Transform is not just some clever math trick. It is a foundational pillar of our digital civilization. It's the silent, unsung hero running on billions of devices every single second, turning chaos into order.